I'm Bruce Bugbee. Welcome to the next installment of a series of talks on principles of environmental measurement. Today we're going to talk about measurement of surface temperature. It's a very powerful and yet very challenging measurement. Many people make errors in this measurement. Our goal is to help you eliminate the errors. I'm joined in this effort by Mark Blomquist. He and I have worked together for more than 10 years trying to make accurate measurements of surface temperature. So you would think you could just take a sensor and put it on a surface and measure the surface temperature. But let's draw a little diagram to show the problems with that. So here's a surface. Now we take a sensor and put it on the surface right against it. And this sensor has some wires coming out to go to a data logger. But as you can see, this part of the sensor is touching the surface and measuring that. Over here, we have air temperature touching all the rest of the sensor. So anytime you do this, it's a combination of air temperature and surface temperature. Now this measurement gets better if you can get a very tiny sensor. It's better, but it's still not the true surface temperature. It's always an average. And then people dig holes and puncture and put sensors in here and do things like that. And now you're measuring the surface plus the temperature behind the surface. So anytime you try and do this with a physical sensor, you can never get the true surface temperature. That's why we use infrared sensors. And on this diagram, I can draw a sensor like this, which measure only the true radiation coming right from the surface. Whether it's a soil surface or a leaf surface or a road surface, it's the true surface temperature. So let's take a look at some of the applications of this. The biggest use of apogee sensors has been in agriculture for canopies to model conductance or irrigation scheduling of plants. Here's a couple of examples in the field. Here's the sensors pointing at a corn canopy. Here's one sensor over a small plant. This has allowed us to precision irrigate crops and determine the water status of plants, precision water stress plants, by measuring the canopy surface. This principle is real simple. Anything that's out of water heats up. If there's plenty of water, you stay cool. You know, we've joked about having a headband and a little infrared sensor pointed at your forehead, like for runners, to tell when they need to drink more water. If their forehead's heating up, they need more water. It's the same thing with plants. So this is a huge application. Another application is predicting snowmelt. Here's high in the mountains. The surface temperature changes rapidly. We want to know how fast that snow is melting and running down for agriculture. This is a huge area of research worldwide because tiny changes in global temperature mean that the snow melts a lot faster. And we get the water earlier and we run out at the end of the summer. We really need to predict snowmelt, and there's many scientists around the world engaged in this. A third application is transportation, icy road analysis. This is in Italy. Here's an apogee sensor off the corner of their truck telling when to put salt down. It's a real-time response telling when to put salt down on a field. You can also use these on a bridge. Danger, ice on bridge. And that's determined by the temperature of the bridge. So there's a couple of applications. Now, let's start looking at some of the key things. Emissivity. This is one of the most challenging things to understand. This is the fraction of radiation from a surface that gets to the sensor. Now, let's back up and go to the fundamental equation that starts all this. This is E is for energy. I can write this, energy equals a constant called sigma. This is the Stefan Boltzmann constant. You can look it up. this is multiplied by temperature. So this is pretty simple. If this is a constant, energy is proportional to temperature. If the temperature goes up, the energy goes up. This is fundamentally how we tell radiation from a surface, is the energy emitted from it. Here's where it gets complicated. This is temperature in Kelvin. So a 1 Kelvin temperature is about 300 in a room. A 1 degree C change is only 1 part in 300 parts. So it's a small change in energy, but this is one of the few things in science that is raised to the 4th power. Kelvin temperature raised to the 4th power is energy. So obviously this is a very nonlinear thing. We've got graphs on the website that show this exact relationship. So it gets more challenging. Let's touch this up a little bit. We had an equal sign here. This is only true for an object that is infinitely black, and it radiates all of its energy to the surface. A third parameter, I've hardly got room for it, but you get the idea, is emissivity. This is a number that ranges from 0 to 1, and it's a multiplier times this whole thing. So we need to know emissivity of the surface. That's characteristic of the surface. Then we put this constant in, this sigma, and then we solve, based on the energy, we solve for the temperature of the surface. This is called the Stefan-Boltzmann law. Boltzmann came up with it, Stefan added to it. It's fundamental to all radiation physics. You don't need to know this law to use them, but it helps to understand the principles, particularly this idea of emissivity. So let's take a look at emissivity. To get accuracy, we custom calibrate every sensor. This is 12 sensors in a complex oven that controls temperature, and they're further controlled here. The sensor bodies are controlled at one temperature, the target's controlled at another temperature. Every single sensor is custom calibrated using this device. But, so if we know temperature, we can get radiation. But when we point these at something, we need to know that they're pointing at something very black. So let's take a look at how black that is. Now this is the errors, by the way. They're specified at plus or minus 0.2 degrees. This is a typical 12 sensors. This 2 times the standard deviation is only 0.12, so it's a generous spec to say they're plus or minus 2. And look at the temperature range from minus 30 up to 65, 70 out here. So they're calibrated over a wide temperature range. This is replicate sensors on top of each other. So now let's take a look at that black body. We take the top off. This looks like a hole, right? This is not a hole. This is a cavity that's painted very flat black. It's a cone-shaped cavity, and it looks like it's a hole. You could put your hand in it, and that's what's called a black body. So a black body has an emissivity very close to 1.0. In fact, nothing really can theoretically get to 0.0. So this black body is more like 0.999, and that's how we calibrate the sensors against this black body, keeping it purely black. So now let's go back to this concept of emissivity, or forward to it. Here's a typical surface. I'm going to show you some emissivities in a minute. A plant canopy can have an emissivity very close to 1. So, wow, that's so close to 1, let's just call it 1 and call it good. But 98% of the radiation comes from the surface, and now let's look at where the rest of the radiation comes from. The other part comes from the sky. And this part right here, this tiny arrow, is 0.02, or 2% from the sky. So this sensor is averaging, in some cases, a very cold sky temperature with the temperature of the canopy, and it's important to correct for this in the software of the sensor. This is well characterized. We know the typical emissivities of canopies, so we can use this to pinpoint measurements. There's the equation. Fraction reflected is 1 minus the emissivity, so it's 0.2. Okay, this is the correction factor. We need to know, this is the equation, but it's more important to know the inputs. Measured temperature of the sensor, that's this temperature right here. Background temperature up here is the sky temperature in degrees C, and then we need to know this. Now we typically look this number up, we measure this, and we can solve for the canopy temperature. I'm not going to go into the details of this equation right here, but suffice it to say that this is well described on the Apogee website, and we've described it in manuscripts we've written. The take-home message is all objects measure the object plus averaging in some of the background temperature. And if you keep that in mind, you realize the errors you can get into. Okay, so let's take an example. Clear day, 25 degrees measured. The background is minus 40. So that's a typical background of a very clear sky. The infinity of outer space is 0 Kelvin. So that tells you why we get such cold sky temperatures. Emissivity 0.98. What we measured was 25, and the actual surface temperature was 25.95. Almost a 1 degree C error if we don't account for emissivity, even though this is very high. Let's take a cloudy day on here. 25, now the sky is much warmer, and this error is much smaller on a cloudy day. So again, these are examples of why it's so important to correct for emissivity. Okay, let's look at the field of view. All sensors have a cone-shaped field of view. Here's the target right here. And it's critical to understand what you're looking at. So to do the trigonometry of this, we called this angle here and this angle here, and now we've got a right angle, and this is the half angle here. So this describes how big the target is. Apogee describes this in two ways: the ratio of the distance to the target diameter. So this ratio, you don't need to know trigonometry to understand that ratio. We also describe it as the half angle right here, this distance here. Apogee sells a series of sensors at different fields of view, but it's imperative to know what you're looking at, because you do not want to be averaging the sky, the sidewalks, other things off on the sides. It's important that this be small, but it's even more important that we know what we're looking at. So this is described in two ways: distance to target divided by target diameter, and then the angle. So let's take a look at the area that is measured with this. Depends on three things. This field of view that we just talked about, obviously mounting height. The higher up, if this sensor is up here, we're the same field of view, we're going to see a much larger circle. So that's the second parameter. And then the angle. We don't always point these down. Sometimes, and often, we point them like this, and now it sees an oval shaped out here. So these three parameters determine what we're looking at. And the next slide walks you through this on what we see with these. So this is example. Here's one that was 22 degrees field of view. Here, this is one of the Apogee sensors. So let's look at the field of view options. These are 1, 2, 3, 4 options that Apogee offers for fields of view. And this is an example over a target. Narrow, medium, wider, and then rectangular. And again, the rectangular, we don't want to see any sky, we don't want to see any ground. Because this is important, Apogee has a field of view tool that is on this website right here. You can find this on the Apogee website. That you put in the type of sensor you have, the model number, it'll tell you the angles, and then it tells you the area that's integrated by that, by doing a bunch of trigonometry calculations. It's just a worksheet. You type in the inputs and it tells you the area. All of these are really to help you fully understand what you're looking at, what's in the field of view, what's not. It's important to be sufficiently narrow, but it's important not to see bad things. Okay, so these are the 4 options, pictures of them. Here's that rectangular, narrow, medium, wide. These are on the website, but it lots of options to pinpoint what you're looking at. Okay? Next critical thing is the infrared spectral response. Sensors can cover a wide range, but it's important not to measure water vapor in the air. We want to see right through the atmosphere, right to the surface. Lower quality sensors measure much of this radiation, and this slide shows us some of the interferences from these things on here. Water vapor interferes right here. This is water vapor in the air. We do not want to measure the water vapor in the air. We want to see right through it. And I think we've got over here carbon dioxide in the air, has bands down here that absorb, but there is this atmospheric window, as it's called, 8 to 14 microns, in which neither water vapor nor CO2 interfere with the infrared signal. So the Apogee sensors are calibrated just to measure this wavelength, which means they can see through many kilometers of atmosphere because it's very transparent. This is something that defines the sensor, defines how it's calibrated. It's not, once it's done, all you need to know is it's calibrated to utilize the atmospheric window. It's not something you need to know when you're on a day-to-day basis when you're using it, except when you correct for the emissivity. It's important to know that it does atmospheric window. Okay, so what do we do when we're trying to measure a canopy and it doesn't cover all the ground? This is a common problem. You can't just point it at the plant. Now, if we put it right here, we could get it so it's only the plant, but plants move around. We want to average bigger areas. It's not possible to always have it right be above a plant. In this scenario, this fraction of the radiation is from the ground, and this fraction's from the plant. So we got a case of partial canopy cover. What this is measuring is both of these together. To solve that, we put it on an angle. And now the same field of view, look at this. All plants. It doesn't see the ground. This is only possible with a narrow field of view, so you can see out over the top of a field. So this is a common application to mount it at an angle so you only see the plants. Now there are still cases with young plants where you see some of the ground, and the next slide shows that. To separate the ground from the plants, we measure the soil temperature. I'll put degrees C right here, and this degree C plant, and then what we measure up here, and we mathematically separate out the plant temperature from the signal here and the measured soil temperature. And this is the approach: fraction of canopy, fraction of ground. It's possible to calculate these fractions, and we have some manuscripts that explain doing this. It's a common problem. Okay, here's the equation: temperature of the canopy. This is all to the 4th power, all done in software in the data logger. Temperature of the surface, temperature of the soil, calculating the canopy temperature. Okay, so now let's start using these to calculate what we call canopy stomatal conductance. If we point these, if we put a sensor right here, and we point it at this leaf, seeing the leaf, let's say the leaf is slightly above air temperature, 2 degrees above air temperature. We write in our notebooks, oh, this leaf is water stressed because the leaves are hotter than the air, and that would be correct. But now the wind comes up. Here's conduction and convection. The wind comes up, the leaf cools off. Well, we write in our notebooks, oh, the water stress went away. It didn't go away. The wind started blowing. So we have to measure and correct for the effect of wind. The sun goes under a cloud. We have to measure and correct for the effect of wind speed. We also have to measure the relative humidity of the air. That determines the driving gradient. If the air is humid, the plants are going to warm up. They're not out of water. They just can't cool from transpiration as fast. So all of these parameters in here are necessary to pinpoint water stress for plants over a wide range of environments. This is an example slide that we use to show this. And the overriding equation for this is Rn, which is net radiation. That's the sum of this outgoing short wave, incoming short wave, incoming long wave, and over here, leaf radiation. These 4 are all go into net radiation. That equals transpiration, and I'll put a T for TR for transpiration, plus conduction and convection. And usually that's called H for conduction and convection. This is a simple equation, and by measuring all these, we pinpoint the water status of the plant. So let's take another look at this in another diagram. This is a lot of equations, a lot of math, but this is where this comes from. This is from this manuscript by Mark Bonquist, our colleague John Norman at the University of Wisconsin, and myself from 2009. It's a paper that works through all of this, and I refer you to the paper for details. But here's that equation I just drew right here. Net radiation, H is for conduction and convection, delta E is for transpiration, and this is photosynthesis. Some of the energy goes into photosynthesis in this equation, and we account for that. This H here is further broken down into the canopy to air temperatures times conductance. That gives us H. It's further broken down into transpiration. This difference here is saturation vapor pressure. So we measure these parameters, calculate transpiration, and this is canopy and stomatal conductance to get GT canopy stomatal conductance. These are all the parameters necessary to measure that. It's a lot of parameters, but the information is extremely valuable. So we take these equations and substitute them all in this, and this is part of Mark's excellence in advanced algebra, and we get an equation that integrates all of them here. This is canopy stomatal conductance mathematically into all of these. I don't know if I can erase my line there. So this equation is all done in data loggers with these inputs, and we've done this now over many fields to pinpoint water status, and I'd like to show you some of that data. The next slides show that. The advantage of this, it's a physiological variable related to stomatal conductance, and everything's in here. It can work anywhere in the world as long as you have these inputs to it. So let's take a look at some of these examples. This was in Nebraska a couple summers ago. We'd have a model that gives us the potential stomatal conductance. If the plant is well watered, it should transpire at the potential rate. You can see here's day and night. And day and the night, the stomates are closed. Some of these aren't smooth because there was clouds, so and other parameters. And this is our measured from our measured parameters. So what we calculate is the ratio of these two. How open were the stomates? This is canopy stomatal conductance in moles per meter squared per second, a fundamental measurement. The ratio of actual to potential, and that's what this is. The potential should always be 1. Now here's some cases where it got above 1, and we think this was wet leaves that made this go above 1, because obviously you'd never get above the potential. But look what happens after a rainfall. Here, it gets less, and now look at what happens in the day. It also went down during the course of the day. There were more open in the morning than the evening. Further down as they dried out. Then, let's look at, this is the slope of this. Now let's look at what happens right here. Another rainfall, 20 millimeters of rainfall happened right here. The stomates jump back up to their potential and even slightly above. And then they started that downward march again. This is the power of using infrared thermometry to sort out the water potential and the stomatal conductance of the plants. This is the average conductance of all of the leaves in the field of view of the plant. And it's an automated measurement, can be made day after day. All right, let's look at our next parameter. This is a graph now of potential canopy stomatal conductance and actual, and here's our 1-to-1 line. If they're always near the potential to fall on that line, they're close to this. And the other environmental parameters affect this: humidity, wind, solar radiation. But each case, they're close to their potential. What happened up here? This is, we think, wet leaves. When the leaves are wet, we get numbers that are above 1. It's just a few values, but this shows the power of this technique for pinpointing water stress in plants. We have just a few more slides. A conclusion: canopy temperatures can be used to determine plant canopy water stress, and in this example, canopy stomatal conductance. There's simple methods to do this, and complex methods are the ones I've described here, where we measure all the parameters and account for all of them. The complex measurements work over a wider range of conditions than the simple measurements. Emissivity, that correction for that can be significant. So we measure sky temperature and mathematically correct with that. And then field of view, we talked about that. Partial canopy cover, we need to sort that out. This is the reference to the paper we're talking about. Apogee can give you copies of this. It's on the website. So this shows the details of making this measurement. Now I got one more slide that I want to talk about. Maintenance of these sensors. It's one thing to get a new sensor and get accurate data, But how about week after week, month after month, getting accurate data? 3 things cause problems. 1, optical path interferences. This is all true of all radiation measurement instruments. Spiders right here can make a nest inside this window. And some places never see this. Other places have a lot of spiders. So there's a spider nest inside that window. When that happens, the sensor suddenly flatlines. It just starts reading its own temperature. So you can tell when it happens. And you get in there with a Q-tip. And this is so important that Apogee sells these scientific Q-tips with this. Put it right in that sensor. You can clean that right out. You can also use some methanol to further clean this. Sometimes it can be helpful, or just water. But you got to keep that sensor clean. Second thing is calcium deposits. When sprinkler irrigation blasts this thing day after day, if it's being hit by moisture, it doesn't hurt the sensor. This is very waterproof, but it evaporates and it leaves a little film, a hard water film, on the inside window of the sensor. Only happens when you have water shooting up on it. That evaporates, you get this film. People sometimes use things like Windex to get that off. That doesn't help, not at all. You have to clean calcium with a dilute acid. And in fact, it doesn't even have to be that dilute because the sensor is very rugged. And again, take the Q-tips, dip them, and vinegar can work, or a dilute acid. You can clean it with acid and it comes right off. Don't try things like acetone to clean it, because that doesn't clean off salt deposits. The third biggie is dust and dirt. This happens in all windows, happens in the windows of your house. This you can clean with window cleaning products, like ammonium cleans this. You can use methanol, even acetone in here. The key, don't push too hard because you scratch the window. Let the chemistry clean the window, not mechanically screen it. Here's the Apogee website that talks about caring for this Apogee radiometer. So that's the summary of the principles of making this measurement, the things you need to watch out for. You can spend your life getting better and better at this, but you can see, I think, that this is a very powerful measurement. We're excited to work with you to help collect better data. Thanks for listening. I'm Bruce Bugbee. Welcome to the next installment of a series of talks on principles of environmental measurement. Today we're going to talk about measurement of surface temperature. It's a very powerful and yet very challenging measurement. Many people make errors in this measurement. Our goal is to help you eliminate the errors. I'm joined in this effort by Mark Blomquist. He and I have worked together for more than 10 years trying to make accurate measurements of surface temperature. So you would think you could just take a sensor and put it on a surface and measure the surface temperature. But let's draw a little diagram to show the problems with that. So here's a surface. Now we take a sensor and put it on the surface, right against to it. And this sensor has some wires coming out to go to a data logger. But as you can see, this part of the sensor is touching the surface and measuring that. Over here, we have air temperature touching all the rest of the sensor. So anytime you do this, it's a combination of air temperature and surface temperature. Now this measurement gets better if you can get a very tiny sensor. It's better, but it's still not the true surface temperature. It's always an average. And then people dig holes and puncture and put sensors in here and do things like that. And now you're measuring the surface plus the temperature behind the surface. So anytime you try and do this with a physical sensor, you can never get the true surface temperature. That's why we use infrared sensors. And on this diagram, I can draw a sensor like this, which measure only the true radiation coming right from the surface. Whether it's a soil surface or a leaf surface or a road surface, it's the true surface temperature. So let's take a look at some of the applications of this. The biggest use of apogee sensors has been in agriculture for canopies to model conductance or irrigation scheduling of plants. Here's a couple of examples in the field. Here's the sensors pointing at a corn canopy. Here's one sensor over a small plant. This has allowed us to precision irrigate crops and determine the water status of plants, precision water stress plants, by measuring the canopy surface. This principle is real simple. Anything that's out of water heats up. If there's plenty of water, you stay cool. You know, we've joked about having a headband and a little infrared sensor pointed at your forehead, like for runners, to tell when they need to drink more water. If their forehead's heating up, they need more water. It's the same thing with plants. So this is a huge application. Another application